on chapters 21, 22, 23. So I started 23. I'm way into it. I like to do just a couple more things today, and then we're done with that. So, we talked about electric potential energy, the relationship between electric field and electric potential. What I didn't talk about is
Forget it then too. Only when it's needed.
okay, so we talked about electric potential, right? Generated by a point charge, kq over r. It's a scalar quantity, not a vector quantity, right? This electric potential is used to calculate the electrical potential energy about the other charge that comes in here and interacts with this charge. If you have an assembly of point charges, and you want to know, suppose you have an assembly of 3 point charges, Q1, Q2, Q3, and you want to know what is the total electric potential that they generate over here. Well, electric potential is not a vector quantity. So you just calculate the electric potential here, that scalar quantity, generated by this charge, this is R1 away, so that will be KQ1 over R1. And then you add it to the electric potential there, generated by the other charge, KQ2 over R2. And then you add it to the electric potential generated by this other charge at that point, plus KQ3 over R3. And if you have more, you just add them up. You don't have to take X components, Y components, because electric potential is not a vector quantity. So it is harder to calculate electric fields in that sense than electric potential. Electric potential is just KQ over R. The K is a constant. This R is a distance, which is a positive quantity, and then if the charge is positive, then this will be plus whatever the charge is, and if the charge is negative, then it will be minus whatever the charge is, right? So you just invoke what's called the superposition principle, where the electric potential at that point is the sum of the electric potentials there, but it's a scalar sum, right, of all those scalar quantities generated by all the charges. Now, what I'd like to do today is, what happens if you have an object that has charge distributed throughout the object? How do you calculate the electric potential generated by it? So last time, I went over the calculation for the electric potential at some point generated by charge distributed over an object, but using the electric field produced by that charge distribution. So there's a connection between the electric field vector produced by the charge and the electric potential produced by the charge. We started with dV equals minus E dot dr, and then if you know the electric field, then one can find out electric potential or electric potential differences. That's one method, right? And for some problems, that is a more convenient way of calculating electric potential. And I'm gonna do some examples today. Again, where we use that idea. Another approach is, what if the problem is such that it's not so straightforward to calculate the electric field first, and then use that to calculate the electric potential. So for some problems, it is just more convenient to directly from the charge calculate the electric potential. And we use the same technique that we used back in chapter 21. If you have charge distributed, like in a ring or a disk, for some geometries, or a rod of finite length, where you can't use Gauss's law, in those cases we use k dq over r squared. Then we have to generate the integral and evaluate the integral. So for some problems, we do something similar. We think of all of this charge here as, maybe the total charge is capital Q, and then we divide this total charge into infinitesimal charges, dq. So think of this dq as like a point charge. And then you say, well, the electric potential that this point charge generates at this point is k dq divided by this r. But then you need to calculate the electric potential there due to the other point charges or infinitesimal charges that makes up this total charge. So you do the integral. So I like to do that today. Except that these calculations tend to be easier because you don't have to worry about, the symmetry. You have cancellation of components like you did in the case of calculations of electric field. So this turned out to be easier. So I'm going to do that type of calculation. I like to start with that. Then we talked about electric potential energy, how that's connected to electric potential. We talked about the relationship between electric potential and electric field. Introduce some language related to that. And then, if you consider the motion of a charged particle in some electric field or region, then applying the work energy theorem, it's basically a conservation of energy type of problem where you have the kinetic energy plus the electrical potential energy being constant. Because for most of the problems that we consider, you don't consider frictional forces acting or normal forces acting, or somebody pulling, somebody pushing, a rope pulling the charge. Usually, you consider the motion of subatomic particles, an electron, a proton, right? When they are released at some point and then they travel only under the action of the electric force from one point to another point, but the electric force turns out to be a conservative force. And so energy is just conserved, where energy is defined as kinetic plus electrical potential energy. And we discussed that last week. I considered the case of a point charge that is fixed in space, and then we calculated the electric potential at various points, and then I brought in another charge and I put it 1 meter away, 2 meters away, 3 meters away from the fixed charge. And then if I release it from rest at one point, how fast is it moving when it gets to some other point? So, we discussed that. And we just used conservation of energy, where energy was given by the kinetic energy plus the electrical potential energy. And that's it. So what I want to do today is I want to do a problem where we calculate electric potential by doing an integral. And another problem that I would like to do is calculating potential differences between 2 points where we can use, where we can use the electric field knowledge. So essentially, let me see, maybe I have some examples over here. Extra examples. Okay, before I do that, let's do this problem. So, what if we have a ring? So let's call this an example. And we have a ring. So this would be a ring of radius, should we call it A? And total charge, Q, uniformly distributed. So what is the potential generated by this charge somewhere on the axis of the ring at a distance x from the center of the ring. So imagine you have a ring like this, right? And charge is distributed uniformly throughout this ring. So there's charge in this ring. The total charge is Q, let's say plus Q. The radius of this thing is A. And I want to know what is the electric potential somewhere over here at a distance x from the center of the ring. You know, here the center over here, this is x equals 0. Right. Yes?
Just to be sure, when we're saying ring, it's usually like a circle, right? It just looks like an oval because of like the perspective.
Right, so it's like this ring.
Yeah.
And I want to know what is the electric field, the electric potential at some point on the axis of the ring, where that point is at a distance x from the center of the ring. Right, so it's just that I cannot draw this
Circular and have an axis.
coming out like this, right? So it's kind of like a side view like this.
Okay. Thank you.
Not quite a side view, but at an angle. We understand the problem? We did this calculation where we found the electric field over here. For this problem, you cannot use Gauss's law. Remember in chapter 22, what were the geometries where you could, calculate electric fields generated by charges distributed in these geometries? Those were point charges, spheres, infinitely long cylinders or wires, and infinitely large sheets. This is none of those. This is none of those. So, well, what we can do is we can then think of all of this charge, capital Q, on this ring, or radius A, right? And it's uniformly distributed throughout. And we can break up all of this charge into infinitesimal charges, which we call dq. Each infinitesimal charge is dq. So if I consider an infinitesimal charge over here, I can say that's dq, and the length over which that charge extends, this length over here, we can call it ds. So the charge dq extends over the length ds. So they're infinitesimally small, and that's why we use d as dq. We could just call them q and s, but the word infinitesimal, so we use this language. Now, what is the electric potential generated at this point here, at this point, which is at a distance x away from the center? What is the electric potential there generated by this charge dq? Only the dq. So I call this distance here r. So what will be the electric potential over there? Well, it would be called dV. So dV is the electric potential generated by the charge dq. So what would that be? If you think of dq as a point charge. What's that?
KQ over R squared.
Uh-uh. So no square in the denominator.
Not as an electric field?
No, it's electric potential.
Oh.
And another thing, it's not kq over r. What is that charge? dq. So it's k dq over r. Get it? Yes, I mean, if I have a charge, if I have a point charge here, q, and I want to know the electric potential here, right? That would be k, the constant, times the charge, which is q. In that case over there, it's dq, divided by the distance from the charge to where you're calculating the potential, which is r. So all I'm doing is I'm calling this d, so therefore this is d, and therefore this is d, like that. That's all I'm doing. Right? And I don't have to say it's away from the charge because the charge is positive, or towards the charge because the charge is negative. Because the electric potential is not a vector quantity, so I don't need to say that. It's just k dq over r. That's it. Now, that's the electric potential at this point generated by this charge dq. What I want is the electric potential there generated by all of the charge dq. So I need to add to this the contribution to the electric potential from the next dq, and then the next dq, and then the next dq, all the way around the ring. And that's what an integral does for you. An integral does that sum. So if you write this expression, dv equals k dq, with the understanding that this is the electric potential there, just generated by dq, if I want all of the potential due to all the charge, then I gotta do the sum. So I integrate both sides, right? Yes? I mean, you have to understand what the integral is doing for you. It's doing that sum for you. And the integral of dv is just v. K is a constant. Now, is r a constant if I choose different dq's on this ring?
Yes.
Will they be at a different distance from the center?
R will be constant because it's the same radius around.
So you have like a cone. So it doesn't matter where you go, right? It's always the same distance, r. Because I'm looking at somewhere on the axis of it. So then r is a constant. And then I have the integral of the cube. But what does this mean? You may know how to evaluate that, but what does it mean? It means the sum, the integral is the sum of all the dq's. This is the sum of all the dq's. And if I add up this dq to the next dq, to the next dq, to all around, what will be the sum of all those charges?
The total charge?
The total charge, capital Q. So the electric potential is given by K, capital Q over R. Now, was I given R in the problem? No. I was given an A. I was given a charge Q. I was given a distance X. There was no R. The R is something that I introduced. So it is something that I need to get rid of. Because that wasn't given. Right? So, very early on in physics, I learned a lesson. And it hurt me. But it's okay because I learned my lesson. So, when I was I graduated from high school, went to college. My first semester in college, I took physics 185, I'm sorry. Except we covered the first 20 chapters instead of the first 16 chapters. And then my second semester, I took we started with chapter 21, and we went through chapter 40, which is essentially physics 280 and 285. That was my first year. And then, as a physics major, in the second year, you take a whole year of classical mechanics. which is like, F equals ma, more torques, and so on, and friction, and so on, which is like part of physics 185, but over a whole year, more advanced. And we also take a whole year of electromagnetism, which is like physics 280, but a whole year worth of it, right? And in my very first exam of the electromagnetism course, there was a problem where, I remember the problem actually was like this, and then there was like part of a ring up to some angle, beta I think it was called, and we were given that, right? Some distance, I don't know, you can call it whatever, A if you like, and the question was, what's the electric field over here? It's something that we can do with what we talked about, right? So what I did, you had to say, okay, so this is, this is the Q, right? The length of it there is the S, right? And then I define the charge per unit length lambda. And then I did the problem, right? And at the end, my answer had lambda in it, which wasn't given in the problem. It's something that I introduced. I said what it was, but I didn't get rid of it in my final answer. And I remember I lost 2 points for that. I remember that in that test I got an 88%, but I could have gotten a 90 had I not lost, 2 points. So, my answer was correct, except that it was expressed in terms of something that I had introduced, not something that was given. And so in that very first exam, I learned that lesson. Always express your answer in terms of the given quantities or fundamental constants. Not in terms of quantities that you introduce, not in terms of variables that you introduce, right? And so, having lost those 2 points, I could have argued, well, but it's here. I'm telling you here what lambda is, right? But I didn't argue at all. But I learned my lesson. From that point on, I never did that again. Every time I was given a problem with rhos and whatever, or sigmas, whatever was given, R's, I always double check my answer to make sure that it was either expressed in terms of constants, fundamental constants, like K. K wasn't given in this problem, but it's okay to give an answer in terms of Coulomb's constant. It's a constant, right? Fundamental constant. Or the given parameters, not parameters that I introduced. So this is a correct expression, right? It's KQ over R. I'm showing what R is, but R was not given. So I should not express or report this as the answer. What should I do? Get rid of R. So what is R? Yeah, so this R is that, right? So the answer is to this problem is that the electric potential, I'll write it over here. At that point is Coulomb's constant times Q divided by the square root of x squared plus a squared. So you can think of this V as a function of x. You tell me x, just tell me how many meters away from the center of this ring you want me to calculate the electric potential. I'll plug it in there and I'll tell you what the electric potential is. So I learned my lesson. If he had not deducted a couple of points here, I probably wouldn't have learned the lesson, and I would have kept doing that again and again and again. But I learned from it. I never did that again. That's the electric potential here, generated by all of this charge distributed over this ring, uniformly distributed on radius A at a distance x, some point on the axis at a distance x from the center of the ring. Now, any questions on this? Look, this is not so bad, right? Tung, 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 boom, we got an answer. I mean, yes?
So for the ring, for the second step, you have R as a constant, but what about a disk?
I'm gonna do the disk next. it will be different because as you consider various rings, the distance r is going to be changing. And that we did that problem also for the electric field. But now, any other questions? Now, remember that we talked about this expression the other day? Something like this that looked like that? Now, in this case, the electric field is changing with the electric potential, and the electric field is changing with the distance x, right?